Okay, so probably we can start. Let me check if there are, there is some participant. Okay, Shaolin, do you agree to start?
Yes, yes, please.
Okay, so I will chair the first 4 talks, and the last 4th talk will be chaired by Shaolin Xiong. So we will start with Paolo Soffitta, who will present a very, very, very interesting mission devoted to the soft X-ray polarimetry. It's the first time that a mission like this will be flown, and you know the polarimetry is very challenging activity and observation. So I'm very curious to hear Paolo. Thank you, Paolo, for coming.
Thanks, Filippo. Can you hear me? Yes. Can you hear me?
Yes,
okay.
Yes,
okay.
Yes.
Thank you. I'm Paolo Soffitta. We speak about IXPE, the Imaging X-ray Polarimetry Explorer, an upcoming new window in X-ray astronomy, and some hints for future opportunities. Basically, why we want to measure polarization? We want to measure polarization because in X-rays, the emission process themselves provides polarized radiation, but also if the radiation is emitted thermally by scattering in a spherical accreting plasma like disk, blobs and columns that are common in X-ray astronomy, it's possible to derive a certain degree of polarization, and this allows to determine the geometry of the compact sources. Also, by means of polarimetry, it's possible to detect vacuum polarization birefringent through extreme magnetic field. Unfortunately, notwithstanding this expectation, basically the only high sensitivity measurement available until now is the measurement of polarization of the Crab Nebula, made back in the 70s by OSO-8. And then basically everything was stopped because the technique that were used so far were very limited in sensitivity, like Bragg diffraction and Thomson scattering. However, in 2001, we actually developed a polarimeter based on photoelectric effect. With the photoelectric effect, the emission direction of a photoelectron is emitted preferentially parallel to the electric field of the coming beam. And basically, by using a detector that is capable to image the track produced by a photoelectron in gas, it's possible to derive the absorption point that is related to space, the emission direction of the photoelectron that is related to polarimetry, the energy by summing the content of each peak of the charge in each pixel that is related to energy, and the trigger output that is related to time. So it's possible by using this kind of detector to do energy, space, and time resolved X-ray polarimetry. This is how the detector is made. Basically, it's a gas cell with a beryllium window on a side and a pixelated plane on the opposite side that makes the image of the track, and a multiplication plane called a gas electromultiplier. And basically, in order to measure polarization, we measure a modulation curve. The modulation curve is the histogram of the emission direction of the photoelectrons. And by the amplitude of the modulation, we derive the polarization, and from the position of the peaks, we derive the polarization angle. We can make a phi-tau cos square of this modulation curve, or using Stokes parameter, the two formalisms are equivalent. Unfortunately, in order to measure polarization, we have to measure this modulation curve, in order to have a minimum detectable polarization, there is a level at which we can exclude the hypothesis of absence of polarization in the data. Basically, we see that we need more than 100,000 counts in order to arrive to a minimum detectable polarization of 1%. That is a much larger number of counts with respect to a measurement of a spectral slope and the source detection. These are the top scientific requirements of XP. Basically, the sensitivity of is such that we can measure a minimum detectable polarization better than 5.5% for half a milligram source in 10 days of observation. But since we are going to observe bright sources where the background is negligible, we can increase the sensitivity with a larger flux or with a longer observing time. The energy range of XP is between 2 and 8 keV. Basically, XP has a principal investigator, Martin Weisskopf of Marshall Space Flight Center, that hosts the Science Operations Center. It fabricates the mirror, and it also does the telescope calibration. As he funds the detector system, provides the ground station, and has a role in the development of the flight software by SSDC. Bull is the company that provides the spacecraft and does the integration and test. The polarization sensitive imaging detectors calibrated are Italian contribution by INAF and the NFN, with the contribution of HB Italy as a company. The Mission Operations Center is a University of Colorado. Basically, all XP was designed in order to fit in the fairing envelope of Pegasus launcher. So it is designed to be stored in a stored configuration. Then what happened that during the design, after the design phase, it was selected a SpaceX Falcon 9 launcher for XP. So now XP was already designed, is stored, but there is a lot of space inside the Falcon 9 for XP. Basically, this is XP after the deployment of the boom in space that has a focal length of 4 meters. There are three telescopes made of 3 mirror units and 3 detector units, each one hosting a polarization sensitive detector. A boom connects the mirrors to the focal plane, and there are X-ray shields that, together with the satellite collimator, allow that only X-rays coming from the optics are reflected into the detector. This is the detector unit with the satellite collimator made of carbon fiber on top. In the bottom, you see the boxes containing the gas pixel detector, that is the detector sensitive to polarization, and the electronic boards. There is also a filter and calibration wheel that will speak in a moment, with 7 position and 4 calibration sources in the detector unit. These are the 3 detector units mounted on the top deck of the satellite. And this is an example of calibration source. Basically, we have 4 calibration sources: Cal A, Cal B, Cal C, and Cal D. Cal A is made of 2 lines, one at 2.9 kV and one at 5.9 kV, that are Bragg diffracted by the graphite crystal. So we have a polarized source in flight to check the constants of the modulation factor, that is the key parameter of a polarimeter. And we have also unpolarized source to check for systematics and do the gain calibration. There is also UV filter to shield from plasma ions during the flight, and a Kapton filter that can be placed on top of the gas pixel detector for very bright sources, to do polarimetry for very bright sources. This is the detector service unit provided by HBI that drives the filter and calibration wheel and the thermal control system, formats the data, and does the time management with the use of the PPS. An important contribution is the calibration. This is a discovery mission. Being the discovery mission, it has to be extremely well calibrated. So we made a calibration facility at INAF that actually for each detector unit, there were 4 detector units, 3 flight and 1 spare for each detector unit, run for 40 days, 24 hours a day, 7 days a week. The most of the measurements were performed in order to do measurement of spurious modulation in order to be calibrated, then also measurement, of course, of the modulation factor and other characteristics of the gas pixel detector. Basically, this is the modulation factor as measured during calibration for the 3 detector unit plus 1 spare. That you can see it increases with energy. This is expected because the larger is the energy, the longer is the track, and it's easier to derive the emission direction of the photoelectron. We detected the spurious modulation below 6 kV, so we made a campaign in order to minimize it and characterize it. And basically, the modulation is subtracted on event by event based by the software plane, so it's not visible to the user. The detector, however, are clocked at 120 degrees one with respect to the other in the spacecraft, so it's possible to check if the polarization that we measure is real. The spurious modulation after the clocking is about 0.6% at 2 kV, declining faster with energy. Another way to minimize the impact of spurious modulation is the deterring the satellite dithers with respect to the X-ray sources in order to facilitate the calibration of the spurious modulation. But basically, it's possible to retrieve the angular resolution of the system because of the star tracker. We recorded the position of the satellite on event by event base. Another characteristic are charging. That is basically gain drop of the detector system in order because of charging of the gas electron multiplier, the multiplication stage, and the secular gain. There is a secular gain increase that accompanied by the decrease of efficiency, a Dieger track length, a modulation factor, but this is understood is due to internal absorption from GPD materials of the gas mixture, but it saturates at about 656 millivolts, that is 82% of the expected value at the time of the flight. Since the modulation factor increases when the pressure decreases, basically the loss in sensitivity is minimized by the fact that the modulation factor is larger. These are the 3 detector units connected to the detector service unit for the bench integration at INAF. And these are the mirrors. Basically, there are 3 mirror units with 24 mirror shells that are fabricated as a replica system of electroformed nickel cobalt shell, very thin because we had to cope with very strict weight and volume requirement for the Pegasus launcher, with an angular resolution better than 25-27 arcsecond half power diameter. Another important activity was the calibration of the telescope that we performed at the Marshall Space Flight Center. And we measured the angular resolution and the effective area with the mirror and the detector unit hosting the gas pixel detector. The telescope modulation factor was produced at the modulated X-ray beam, the spurious modulation at different energies. And basically the results of the calibration was that the modulation factor measured at INAF is fully consistent with the modulation factor measured at Marshall Space Flight Center with the optics and the view, stating that basically the mirrors, as we knew, mirrors do not introduce extra polarization. And this is also true for the spurious modulation measured at INAF and measured at Marshall Space Flight Center, basically are consistent. This means that we can fully use the ground calibration that we did and the mirror calibration to infer the joint performance during flight. These are on the left, the three mirror unit at ball before integration. Again, on the right, the 3 detector unit during the integration. This is the satellite without the solar panel with the 3 detector unit, 3 mirrors. And this is on the right, you see the deployed boom with the mirrors and the detector unit on the bottom and the solar panel mounted on the bottom left. The measured performance of the X-ray instrument are basically all within the requirement except the efficiency that for the decrease of the density of the pressure inside is not meeting the requirement, but the sensitivity of the whole satellite remains the same for the reason that I explained before. The observation to-do list is such that we performed the vibration, the shock, the acoustic, we did the functional test, and the thermovacuum test will be performed in a couple of weeks for a launch readiness on 17 November 2021. The data become public after 1 week after the accomplishment of observation through EASARC. They can be retrieved from there in order to exploit at best the data from ICRANet. There was set up a public working group for all the class of sources that can provide polarized radiation. And basically, this is a first year observing plan. There are 33 sources to be observed in the first year, basically on all classes of sources, but not cluster of galaxies. Basically, the total time, as you can see, for each class is very long. This is because we need a lot of counts in order to measure the polarization. As an example of polarimetry, I don't go into detail for each class of source. I just show here what happens for the accreting millisecond pulsar. If we consider the geometrical parameters of the accreting millisecond pulsar, we see that phase resolved flux is not able to disentangle the geometrical parameter of the accreting millisecond pulsar. But this is possible to be done with polarimetry by looking the different behavior of the polarization angle. The accreting millisecond pulsar has a low magnetic field with a high magnetic field. For example, in magnetars that are isolated neutron stars with a magnetic field up to 10 to the 15 Gauss, is possible to detect birefringence from this system with all the possible models of the atmosphere of the neutron star. Close to the center of our galaxies, there are molecular clouds. These molecular clouds are shining X-rays, but they are cold. The hypothesis here was done back in the 90s by Rashid Sunayev. The hypothesis that they are reflecting now radiation emitted from the past when our galactic center was at image N with the X-ray intensity 1 million times brighter. And if it's so, the radiation scattered should be polarized with the polarization pinpointing the origin of the X-ray sources. And so it's possible to definitely prove this hypothesis. Unfortunately, these molecular clouds are becoming fainter. We thought to use Sagittario B2 at the beginning, but now recent study end up to indicate that molecular clouds close to the galactic center can be best candidate like G011 minus 011. Another possible measurement with the XP is the measurement, an additional measurement of the spin of the black hole. We expect that for a rotating black hole, the polarization angle rotation with energy is much more important with respect to a non-rotating black hole. So by actually fitting the polarization angle rotation with energy, we can derive the spin of a black hole. The X-ray band is also very useful for studying blazar because it allows to study either synchrotron dominated blazar and inverse Compton dominated blazars. For inverse Compton dominated blazars, basically we can derive the origin of the seed photons if a synchrotron self-Compton or external Compton. Finally, I just speak very briefly of next opportunities. Basically, after X-ray, there will be XTP that mounts 4 optics at high throughput. There will be 6 times more area than XP. However, the energy band is the same between 2 and 8 kV, so it means that it will enlarge the number of sources for each class. But for the future, for example, for ESA Voyager 50, as a MIDEX mission, basically we proposed to enlarge the band, to going from 0.2 to 15 to 80 kV. This is because with there is somebody that is speaking. This is because basically the enlarging the band is possible to study much better. Sorry, but I cannot. Maybe I can stop here because I cannot.
Comunque, sto cercando di organizzare. Sì.
I'll stop here just saying that basically
una cosa, ho visto alla fine della sessione c'è un talk sui neutrini pubblico, cioè, è confermata questa cosa, e poi dopo c'è la round table.
Okay, I think I finished here just saying that basically in the future there will be an enlargement of the band from 0.2 to 8 kV in order to study much better the polarization of X-ray sources.
Alla fine del talk pubblico.
Okay, I'm finished. Hello? I think I finished here. Can you hear me?
Yes, yes, I can hear you. So
okay, I think yes, I think I'm finished.
Yes, sorry. Very nice talk, Paolo. I think it's really one of the best mission that can give us information about the polarization of the X-ray sources, because I see that there are it's very difficult to measure this this type of quantity, and in the past probably many results are affected by systematics. So it's very important what you have done. So congratulations.
Thanks, Filippo.
Other comments or questions to Paolo? Okay, so if there are no, I would like to just to hear from you which are the mission you have mentioned, some mission already approved, or is mission concept and you have in which you are involved, or you have proposed for the future?
Yeah, basically these are while XTP is in phase B, so will be probably launched in 2027 for ESA Voyager 50. These are missions that have been proposed at as a concept, basically, for the post 2035. NASA for the decadal survey also proposed a probe mission that also has this characteristic to enlarge the energy band from 0.2 to 60 kV. So basically, for the future, we foresee to propose missions that enlarge the band with respect to this narrow band between 2 and 8 keV, for which XP and XTP will measure polarization.
Okay, thank you. Thank you. So I would start with the next speaker, Merlin Cole.
Yeah, so I will try to start
Are
sharing.
you ready? This is another talk devoted to polarization, very interesting. And we have still another by Miguel Moita devoted to prospects for polarization, a very interesting quantity to be measured.
So I cannot start sharing until Paolo stops sharing, it seems.
Stops, okay.
I think he stopped now, so let me try again. Should be there now. Can you see it?
Okay.
Can you see the slides or not?
Yeah, yes, it's okay.
Oh, okay, so I can start, I think. Okay, so thank you for this opportunity to talk about a little bit more about polarization. Compared to Paolo, it will be a little bit higher energy. So this is gamma rays tens to hundreds of keV, whereas IXP is 1 to 10 keV or so. And it will be about one specific scientific target, which is gamma ray bursts. And this will be with the POLAR mission, which was a mission that was launched in 2016. And we finished analyzing all the data. And then there's POLAR 2, which we will launch in 2024. So very short overview of the science case. Very simply speaking, you could say that gamma ray bursts have been studied for a long time, but there's still many open questions like where does the radiation come from? What is happening in the jet? What does the jet look like? Are there magnetic fields? And if so, what is their structure? And these are the kind of questions that have been theorized for a long time that we can answer with polarization. And it seems that despite all the efforts with spectrometry over the last 50 years, we're not much closer to these questions. And listening to some of the sessions from, for example, yesterday on the photospheric emission, it doesn't seem like just spectrometry is going to be able to answer this. So it has been theorized that polarization, you can do this relatively easily. I don't have time to go into the detail on all of these different models. I would refer you to a nice overview paper by, for example, Kenji Toma from 8 years ago from the Huntsville Symposium. But more recently, there's also a more elaborate overview paper by Ramandeep Gill and Jonathan Granault. And they are actually working on yet another one where they also include time-resolved predictions by all the different models. So this is very complex, and I really don't have time to go into that, but simply speaking, you could say that synchrotron models with ordered magnetic fields predict high levels of polarization, around 30–40%, whereas other models with unordered magnetic fields or photospheric emission typically gives no polarization or very low levels. So since it's such a powerful probe to look into these objects, there have been many attempts over the past. I list here all of the publications that were there before POLAR was launched, so before 2016. You see the first ones here from instruments like RESI and EBIS and SPI and BATSI, which were non-dedicated polarimeters. And as such, they had a relatively low sensitivity to this. So the statistical error bars are quite large, as you can see. These are the 1 sigma errors that I mentioned here. But on top of that, they were not calibrated on ground for this. Now, this is specifically an issue for polarimetry because we don't have standard candles in the sky. As Paolo said, we only have one measurement of the crab at low energies, but at higher energies, where we measure from tens to hundreds of keV, there's no consistent measurements of any source available. So you cannot calibrate your instrument once you're in orbit, which means you cannot check for systematic errors. And what has been found detailedly looking at some of these measurements that were performed in the beginning is that these suffer from quite large systematic errors, meaning you cannot really deduce much from their results. Also for details, I would refer you to an overview paper by Mark McConnell from that from a few years back. However, there's been a lot of progress in the last 10 years, starting with the launch of GAP, a small Japanese mission that was completely dedicated to gamma burst polarimetry. It was calibrated on ground and it managed to perform polarization measurements of 7 GRBs. I list here only the 3 that they published. I will later show the results for the other 4, which were upper limits only. So you see the errors are still quite large. It's quite difficult to really conclude anything from those results. But what GAP really did is that they showed that these measurements are difficult, but they are possible. Now, after GAP, there came 3 missions. The first one I list here, which is COSY, balloon bore mission, which was calibrated on ground. It's not fully designed to do polarimetry, but it was shown prior to launch to be able to do this. And they managed to do a polarization measurement of 1 GRB during their balloon flight, and they gave an upper limit. The other 2, Polar and AstroSat, I will later on discuss a bit. First, just a little bit about how you measure it and to show why it's such a difficult measurement. It's similar to what Paulo showed, except in our case, we use Compton scattering of the photons in our detector. So if you have a detector consisting of segmented parts, and you have a photon coming in and it scatters in one of your bars and then it gets absorbed in another bar, you can measure the azimuthal scattering angle. Now, this is interesting because if you look at the Kleine-Shina equation, the equation here in the middle, there's this term cosine squared phi, where phi is the angle between the polarization vector of the incoming photon and the azimuthal Compton scattering angle. So if you measure for the photons the azimuthal Compton scattering angle and you plot a histogram of that for the full flux, you get one of these curves here in the bottom, where if it's polarized, you get this nice 180-degree modulation. If it's unpolarized, theoretically, it's a completely flat distribution. Now, this measurement method shows one of the main issues. It's that you have to measure each photon twice. You cannot simply absorb it. So your sensitivity or your efficiency for these kind of measurements is relatively low, about an order of magnitude lower than a typical spectrometer. It gets worse when you have to do it for gamma ray bursts, because we don't know where these things are going to occur in the sky. So you need a wide field of view, and therefore you get a worse signal to noise. So these measurements really are statistically limited and photon starved. And this is one of the real issues. The second issue is the systematics that I already covered, because, for example, this theoretical unpolarized curve there, it's beautifully flat, but in reality, for example, with Polar, you see the one on the right, which is what we actually do measure when it's unpolarized. And unless you understand all of those kind of variations in your modulation curve, you cannot correct for it fully, and it means that whenever you make a mistake in the understanding of your instrument, you will measure some level of polarization, even if it's unpolarized. So that's really the trick, to measure low levels of polarization, and measuring zero polarization at the end is theoretically not really possible. So despite all of those difficulties, we did try with Polar. So we developed an instrument consisting of 1600 plastic scintillator bars. You see them here on the bottom right. So they're grouped in groups of 8 by 8, read by multi-anode PMT. The bars are made of plastic to maximize the Compton scattering cross-section, because we want to have photons that scatter. We don't want any of them to absorb, or at least as little as possible, because those we cannot use for polarization. And on top of that, plastic allows us to get a relatively large effective area while keeping a low mass. So Polar was only 30 kilos. And then finally, the bars are quite small, so 5.8 by 5.8 millimeter in cross-section, to get a small granularity and therefore high precision on the measurement of the scattering angle and therefore the polarization. So the final instrument from Polar, you see it here in the top right. This was just a few weeks before we launched it. All the plastic scintillators are in this carbon fiber box. The carbon fiber is used as a shield for low energy electrons in orbit. All the electronics is housed in the white bottom part. And in the bottom right, you see a cross-section from simulations and what the measurement principle is. So a photon comes in, scatters in one of the plastic scintillators, which is shown in blue there, gets absorbed in another plastic scintillator. We know the Compton scattering angle, and we can infer the polarization. So the total final instrument was about 300 centimeters squared in effective area, so relatively large in order to compensate the amount of statistics that we need, and has a large field of view of about half the sky. all the time. Now, details on the instrument, I will refer you to yet another paper, but this time by Nicolas Produit, who not only details very nicely all the technical details of this instrument, but also took the time to explain everything that went wrong during the development and how we solved that, so that actually people can learn from our mistakes as well. Because we made a few, but in the end, we did manage to launch Polar. You see it here in the top right. It was bolted on the Chang'e-2, the second Chinese space lab, in September 2016. So if you look closely on this big tube, which was a manned space lab, you see a small little box that is Polar. It was always pointing towards zenith, and so we were observing the sky continuously, and we had no occultation of the Earth. So it was launched in 2016 from the Juchran Satellite Launching Center in Inner Mongolia. It took data until April 2017. At that point, unfortunately, the high voltage power supply that is used for the PMTs failed, which was a real shame because all the other components in Polar still work perfectly well. We were able to communicate with it and do fake data acquisition up until 2019 when Chang'e-2 was deorbited. But without the high voltage power supply, we couldn't continue taking scientific data. So we were left with only half a year. Still, that was quite a good half year because we did detect 55 gamma ray bursts as well as 2 pulsars. And we were able to analyze those. So very briefly, once again, the systematics before I get to the gamma ray burst results, because that's really the main task that we did after launch. We spent about 2 years fully focusing on understanding every little detail of the instrument to be able to convince ourselves that what we were seeing was polarization, if we would see any. So for this task, we went through all the 1600 channels. We checked their dependencies on temperature, time, everything was calibrated very precisely. And once we convinced ourselves of that, we started cross-calibrating the detector using the 3ML framework, which allows you to put data from different instruments together and do joint spectral fits. So in the top right, you see, for example, a fit that we did with the Polar data for a GRB that was also seen by SwiftBUT. And we did a joint spectral fit. So the Polar data is in purple and the BUT data is in red. And the important thing to take away from there is that we don't see any weird systematics, meaning that we understand the instrument quite well. And on top of that, the absolute calibration, so the relative flux measurement that we did was within 10% of SwiftBUT. And also when we did this with Fermi GBM, it was the same, which is about the highest level that you can get, because it's, I think, similar to what you have between SwiftBUT and Fermi GBM. So once we finally convinced ourselves that everything was working and we understood everything, we could go to the polarization analysis, which at that point is actually relatively easy. So I show it here on the left. This is for 14 of the 55 GRBs. 41 of the GRBs were simply not bright enough to do any kind of analysis on to get any statistical significant measurements. But you see here on the right, the posterior distribution of the polarization degree for the 14 GRBs. And you get the quite clear picture that the results really favor low levels of polarization. And for 5, 6, 7 GRBs, we can exclude the polarization above 40, 50% with quite a high significance, whereas the other ones still are completely compatible with a lowly polarized or even an unpolarized flux. You see the same thing in the figure on the right. So the polar points in brown compared to the upper limits from COSY, the 7 results from GAP, and the measurements from AstroSat. So AstroSat I didn't mention yet, but this is an instrument I think that most people know, which has been in orbit since 2015. Still taking data. It measures quite a few GRBs. It has been calibrated on ground, but only for on-axis polarization. But with that knowledge, they should be able to extrapolate their results also for off-axis, which is needed for gamma ray bursts. But I think it's quite clear from this figure, if you look at it, that the AstroSat results do not seem compatible with those of Polar. They've published a total of 11, 12 GRBs, I think, by now, in different kinds of papers. And overall, what they tend to see is polarization levels above 50%, which is really contradicting Polar. And I think it's difficult to convince myself that this is real. So there is something going on either with the Polar data or the AstroSat data. I don't have time to go into it here. Of course, I have my theories, but I don't think this is the place to discuss that. I would just like to say that for the polar data, we have made everything public. Also, the analysis tools are public. You can find it in the link in the bottom left. So the analysis tool is built into the FreeML framework. And I think relatively easily, anybody can reproduce our results and potentially do more studies and look for potential mistakes that could be on our side. So far, we haven't found any. So we just continue to believe that our results are correct, as we cannot do more to study the astrosat ones. If you also look at this figure, and you just, let's assume now that the polar results are correct, we can compare it to some theoretical models. So here I took this from a paper by Ramandeep Gill and Jonathan Kumar from 2019, where they calculate the distribution of the polarization degree that you expect from different models. And it appears that with the polar data, we can only kind of exclude the synchrotron models with a toroidal magnetic field, whereas all the other models are completely compatible with our results. So that's not the most exciting result. It gets a little bit more exciting when we start to do time-resolved studies. And this is something which is particularly, it's a bit peculiar in polarization. It's sort of counterintuitive, because let's say that you have a source, in our case, a gamma ray burst, you chop it up in 2 bits. Both parts are highly polarized, but the polarization angles are 90 degrees different from each other. Now, if you sum the full flux, what you measure in the end is actually unpolarized, because they cancel each other out. So, whereas we with polar seem to see no signs of polarization, it could simply be that there is polarization, but it changes very rapidly during the gamma ray burst. So we looked for this for all 14 GRBs. For 12 of them, we didn't see any signs of this. For 2 of them, we found hints. And interestingly enough, these are the only 2 GRBs in our catalog that are single pulse, fret-like pulses, so a fast rising exponential decay. So only for those 2, we see some hints. The brighter one we studied in a lot of detail together with James Michael Burgess. In the paper that I list here, we have the results. So we have this plot in the top, which is the time-resolved polarization study. After fitting both data from Polar and data from Fermi-GBM to fit both the spectral and the polarization data at the same time. Spectral part we did with a synchrotron model, which seemed to fit very well. The polarization, we just used the polar data, and you see the results here where the polarization is on the radial axis and the polarization angle is on the polar axis. So the results seem to favor a polarization degree on 30–40%, but with a very quickly changing polarization angle. So it's not really statistically significant enough to really claim that this is happening. We see a strong hint, but I would not say that we're super convinced that this is actually the case. But if this is true, then this would mean that within a single GRB pulse, the polarization is actually quite high, but the angle simply changes quickly, thereby washing out the final result. So if this is true, then what I showed in the previous plot is rather useless, because that just is a washed out polarization. So this would really change everything if this is, if we can really convince ourselves that this is correct. Now, unfortunately, we ran out of statistics at Polar. We really cannot do more of the data we have. We pulled everything out of it that we could. So we really have to move to having more statistics. And this is something that we learned when we were finishing our analysis in 2018. And so we started proposing the Polar 2 mission. Basically the same collaboration as Polar, which was led by IHEP in China, University of Geneva, PSI in Switzerland, and NCBJ in Poland. For Polar 2, we have MPE instead of PSI. So largely the same collaboration, but we have our friends in Germany joining us for this. So quite soon after coming up with the idea of Polar, we actually were already accepted for launch in 2024, where we will go to the China space station, which is currently under construction. And it should be finished in 2022, and we will move there in 2024. So the idea of Polar 2, it's an evolution of Polar. We implement all the issues that we've seen in Polar and improve many of the things that we learned that we could improve. The most obvious one is that we got rid of the high voltage power supply. That was the component that failed in Polar, and we can do that by replacing the PMTs, which take about 1 to 2 kilovolt, by silicon photomultipliers, which only require 50–60 volt. Now, silicon photomultipliers have another advantage. they are more robust, so we need less damping material, which means less dead material around the detector. They are, more importantly, more sensitive as well. So their photo detection efficiency is a factor 2 higher than the PMTs that we use in Polar. And finally, because of their design, we also have less optical crosstalk in our measurements. So you see an array that we plan to use in one of our prototypes. So it's an 8x8 array of silicon PMs. Each pixel is 6x6 millimeters. And so similar to Polar, we read out again 8x8 bars at the same time in what we call a detector module. The downside of silicon PMs compared to PMTs is that they have higher noise. So the dark noise is an issue, but this you can fix if you go to lower temperatures. So for this purpose, we're going to cool the silicon PMs with Peltier elements. So we're working on that in the lab now. You can see some prototypes that we're building at the moment and testing where we have a Peltier element stuck to the bottom of the silicon PM array that you also see on the right here. So on the right, you have the silicon PM array in the bottom, the front-end electronics on the left, and then the Peltier element is pushed towards the bottom of the side PM array. The front-end electronics, we're getting the first ones, I think, in 1 or 2 weeks. So that's very exciting when we get those, because then we can continue to play with actually the final version of the electronics. On the front end, we have 2 CityRock ASICs, which read out the side PMs. We use an FPGA, which handles the control of the trigger logic of the individual module and the communication with the backend electronics as well. Additionally, it does the high voltage control of the temperature, and it also controls the Peltier to stabilize the temperature inside of one of these detector modules. So as I said, the detector module has 8x8 channels. In total, we're going to have 100 of those. You see here again a schematic representation of one with the scintillator bars in the bottom and the cooling system in the top, which also has the electronics in there. We, of course, already have some prototypes, which we're testing heavily in the lab. We have about 4 of them now to test the different kinds of scintillator that we thought to be used and test the performance of the silicon PM. And everything is actually even slightly better than what we expected. So this is very good news compared to the performance of Polar, where we got 0.3 photoelectrons per keV deposited in the scintillator. With the first prototypes, we get 1.6 photoelectrons per keV. You see this in the bottom left, where we have the light yield measured in the lab of one of these 8x8 arrays. You see it's not very uniform. We're still working on that. This is due to some misalignment issues in the mechanics, which we're improving at the moment. And overall, we expect that we get an average light yield of about 1.6 photoelectrons per keV, which really improves things specifically at low energies in our response. On top of that, compared to Polar, we reduced the optical crosstalk by a factor 10, about. In Polar, this was used because the multi-anode PMTs that we had have one thick glass window, and light can travel through this glass window from one channel to another one, which was quite a problem. In silicon PMs, this is completely gone, and we only have a little bit of crosstalk from traveling from bar to bar. So finally, all of these changes also improve our M100s parameter that Paolo already introduced, so the sensitivity to polarization, especially at low energies. This is very significant. So taking all of these first results from the lab into account, we can get an idea of our effective area for polarization. So the effective area that I show you in the bottom right is a function of energy, only is for the polarization events. And you see it compared to Polar in green and Polar times 4 for your convenience in red. So you can see that by making the instrument 4 times bigger, so we went from 1600 scintillators to 6400, we gain quite a lot, but you can see that the technological improvements by going to side PMs and other small changes really gains us a lot at low energies, where of course there's a lot of photons, and where some models predict that there's energy-dependent polarization. So we can also start to probe that with Polar. So apart from the polarization part, we will also, of course, detect lots of photons that we cannot use. So our total effective area is almost a factor 2 larger than what I show here, which means that Polar 2 will be extremely sensitive. And using the computing power of the China space station, we will also be able to send alerts to ground within hopefully minutes with some rudimentary localization that we can provide, because we also will have some dedicated spectrometers on board, which can do both the spectral measurements and the localization of every transient that we see. So finally, just to transform all of the parameters that I mentioned into performance, in the bottom right, you see the MDP, which Paula also introduced. It's the minimal level of polarization that one can distinguish from being non-polarized with a certain confidence level. And you see it here in log scale, and on the x-axis, it's the fluence of a GRB. So we compare Polar 2 with Polar and GAP. You see that GAP was able to probe the region with very bright GRBs down to maybe 10% polarization. With Polar, we already made a step, and we were able to do get things down to about 10–20% for a few GRBs per year. In Polar 2, we really make a big step. And for example, very weak GRBs like 1708, 17A, we can almost do polarization there. Not really, but GRBs with a fluence of 10 to the -6, for sure we can do something. At 10 to the -5, we can start probing very precisely below 10%. So we expect about 50 gamma ray bursts per year that we can measure with a precision better or higher than the best 5 that we did with Polar. And on top of that, we will also help the wider community by sending transients alerts within a few seconds everywhere, thanks to our large sensitivity. I think that's all the time I have. So thank you very much. And if you have any questions, please let me know. Thank you.
Thank you very much, Merlin. Unfortunately, we have used all the time. If there is some question, you can look to the chat, and probably is the only way, because we need to go ahead.
Okay.
Okay. Thank you very much. Very interesting, and congratulations. And I think that will be a very good mission for that. I have been very, very happy to hear, to see your paper on Polar. In my opinion, is very realistic, the results obtained.
Thank you.
Okay. We have to go ahead with the paper by Lian Tao. Please stop the sharing, Merlin, and Lian will present the paper.
Yes, thank you. Yeah.
Yes, on the chasing of transient constellation hunters. It's a new mission, I imagine.
Yes, thanks so much. It's a new mission and it's in concept stage. Yeah. It's my pleasure to introduce the new mission we proposed. It's the chasing or transient constellation hunter. Why we call it chasing or transient constellation hunter? Because we also call it catch. Yeah, from the name, we can know what will the mission want to do. We will chasing some target. The target is transient, and we will chasing a lot of target. So we call it war. It's a constellation. That means it has a lot of satellites. So here is the brief introduction. It's a constellation include hundreds of micro satellite. Here is a finger. For the constellation, we want to perform follow-up observations for many transient simultaneously. So in this constellation, each satellite will carry a lightweight focusing X-ray telescope. The constellation will chase transient. And there are 3 types of telescopes, so 3 types of satellites in catch in the constellation. We have one type is imaging satellite, another type is spectrum timing, and we also have Asian satellite. So because we have 3 types of satellites, so we can perform imaging, spectrum timing, and polarizing observations simultaneously. And because different satellites in the constellation can cooperate, so we can perform uninterrupted observations, and we can have different field of view, have different sensitivity. In the future, we can extend it to other energy band. Now we focus on X-ray, soft X-ray band. In future, we can extend it to optical, infrared, and other energy band. Here is the basic parameter of the set constellation. The number of satellites is several hundreds. There are 3 types of the satellite I just mentioned. We have spectrum timing, imaging, and polarizing satellites. The difference between different types is the detector. Yeah, for example, for spectrum timing satellite, it will carry SDD. For imaging, it will carry SDD array. For polarization, it will carry GPD. The field of view of one satellite is 1 square degree. But for the constellation, the field of view is flexible, because we can have, for example, we can have 10 satellites to form a field of view of 10 square degrees. The energy band is from 0.5 to 8 keV. This is the sensitivity. This is the effective error. The planned mission lifetime is 10 years for the constellation, but just for one satellite, the lifetime is 3 years. So we need to replace old satellites. That means we can also have performance upgrade. Why we propose this mission, propose this constellation? Because we know in time domain astronomy, there are a lot of missions. They will discover a lot of transients. For example, in radio band, SKA in optical band, LST in X-ray band, Einstein probe socials, and other multi-messenger instrument will also find a lot of gravitational wave events and high energy neutrino events. Here are some examples what they will find. For example, in X-ray band, social telescope will find a lot of magneta and thermonuclear burst. Yeah, we can know the number is very large. In optical band, and we can also have a lot of transients, and the gravitational wave event will be detected in a large number. So we can conclude in the future, a lot of transients will be detected. But now there is a question, how to perform follow-up observations for so many transients. Let's look at the operating and planned missions. These missions focus on 3 directions. Some missions focus on high sensitivity, such as XTP, and some missions focus on high resolution, and others wants to discover more transients, such as EP socials and so on. We can say there is no telescopes or mission can perform follow-up observations for a lot of transients simultaneously. That means a lot of important science discoveries will be lost. That's why we need a new mission. We need to catch. Here is a comparison between catch and other telescopes. We can look at this point. The most important for catch is that the number of follow-up target is 100 or several hundreds. Here is another comparison. Here is the catch. Here are other telescopes or missions. for catch, different satellite can cooperate, so catch can chase a lot of transits. We can chase hundreds of transits. Also, we can have the full sky coverage. That's also very important. The scientific target of catch are transient events. Here are some examples. For so many transient events, we will perform follow-up observations. Here are also some examples such as gamma ray burst, neutron star, black holes, gravitational waves, supernova, unknown outbursts. How the constellation for follow-up observations, here are some 3 modes. One mode is single satellite can chase or track one or several transits. And hundreds of satellites can work together to monitor a lot of transits uninterruptedly. Moreover, for some very important targets, such as gravitational wave burst, the constellations, the different satellites in the constellation can form a constellation to joint observation the target. Here is the finger. The scientific question of catch, there are 3 levels. For the first levels, we want to have some improvement. The second levels, we want to have some discovery. And the top level, we may bring the revolution. I have some examples. The first case, the case is the first level or the improvement. In this case, we use the capability of catch to achieve uninterrupted monitoring. For example, for crab pulsar, we know it has glitch, but we don't know when the glitch when the glitch happen. And in the glitch, during the glitch, there are something very interesting, such as the delay spin up. If we can monitor the crab pulsar, then we can know when the glitch happen, and then we can produce a name for other telescopes. And for catch, we can do that. Moreover, catch can perform simultaneously spectrum timing and polarizing observations. So that means use catch observations, we can check different models of pulsar glitch, and we can also study the physics behind the pulsar glitch. Here is another case for the first level. We use the capability of the flexible field of view. For other missions, the field of view is fixed, but for catch, the field of view is flexible because we can have different satellites for different field of view. I have this example. If we have if we want to search for the gravitational wave event, the counterpart of the gravitational wave event and or the neutrino events, we can the catch constellation can form a flexible field of view. It can for square array or it can for rectangle array, so it can search the counterpart in this region. Moreover, its sensitivity is high. The sensitivity will be 1 order of magnitude better than the more sky monitors in EP and Celsius. Now I have another example. This is the example for the second level. We want to have some discoveries. I have the example of the magneta. We know last year we found the association of FRB and the magneta. If last year we already had catch can monitor the activity is of magneta, so we can catch the whole outburst, the whole burst. So that will be very important to start this event. Moreover, for catch, we can perform imaging, spectrum timing, and polarization observations simultaneously. So that means we can study the physics behind the X-ray activity of magneta, such as large outburst, QPO, glitch, and anti-glitch, and so on. As mentioned above, we know in the future, socials and other telescopes such as EP will find a lot of magnetas. But for socials and EP, they just have one follow-up telescopes. One follow-up telescope. That means they just can follow up one target. That means many targets cannot be followed up. But when we use catch, we can perform follow-up observations for a lot of magnetas. Then we can perform population study. Now we have the top level, what we want catch to do. Let's review the capability of catch. We can perform follow-up observations for a lot of transient. We can simultaneously measure in. We can perform simultaneous imaging, spectrum timing, and polarizing observations. We have flexible field of view, and we can also have custom-made for some spatial target. That means catch is very complicated to do follow-up observations. That means catch may have some very important discoveries. Let's review the discovery of pulsar. Before the discovery of the pulsar, we don't know the existence of this interesting kind of target, but after their discoveries, it opened a new window in astronomy. So for catch, it will do a complete follow-up observations. So we expect catch may find something important. It may bring up a revolution and open a new window. So for catch is a constellation, we will use microsatellite. Here is a comparison between the satellite in catch and the InSight HMT. The satellite in HMT is very large and expensive, so we cannot use that in a constellation. So we will use small satellite, but small satellite also have their advantage. Their costs are low, they are very flexible, and their developed cycles are short. So they have their advantage, but we all know they have some disadvantage because the satellite is very small, so the effective error is small. But we can use small satellite to make up the weakness of large telescopes. Because for large telescopes, we know you cannot observe a target for a long time, but for small satellite, for catch, we can observe a target for a long time. So small satellite also can have some important scientific result. Here is an example for the polar night we know last year. The product is developed by Tsinghua University. It's just one unit CubeSat. It found the polarization changes before and after the pulsar glitch. It's very important for the X-ray polarization. Here is a design of one satellite in catch. The two fingers are
we have a problem with the audio. with the connection. Thunderbird. Shaolin, can you contact?
Yes, yes, I'm calling her. Philip, she's trying to reconnect again.
We wait or we continue with another? We have some time still, 4 minutes. If she can connect very soon, we can hear the conclusions.
Yeah, yeah, but I'm not sure. She's using her cell phone.
Ah,
But yeah, but I have no idea whether she can connect very soon or take longer.
We wait 1 minute, 2 minutes. Sorry for other people. I don't know. Probably.
I think I saw her just joined.
Okay. She's connected now.
Yes, sorry, can you hear me?
Yes, yes. Please give us the conclusions
Next.
because we have lost some time. Share the screen and go to the conclusions.
Okay. Okay. I just talk at this page slides when that, yeah, this is the design of one satellite.
In a short time, can you conclude? Okay.
Okay, conclude. Okay. Conclude that, yeah, okay. Okay, here I will conclude. Yeah, this is the constellation. Yeah, we have catch the constellation. We have 100 of microsatellites, and for catch, we will perform follow-up observations, and each satellite will carry net with focusing X-ray optics, and it will perform follow-up observations. We will have one satellite. It's the technologic pathfinder. It will test the technology and part of science. We will have 10 more satellites. It will be the constellation pathfinder. It between 2023 and 2030. We will have the full constellation around 2030. Thanks. Sorry for the connection. Sorry for this.
Just a question. The focusing telescope is based on lobster eye concept, or
Yes.
Oh, okay, good.
Yeah.
Okay, good. So with an error field of view, I mean.
Okay. Yeah, here.
The field of view is not so high.
In 1 kV of around larger than 40 square centimeters.
Yes, and the field of view?
A field of view is 1
degree?
1 degree, 1 square degrees, just for one telescope.
Okay. Thank you very much. Thank you very much.
Thanks so much. And sorry again.
No, nothing. Okay, we go ahead with the paper by Enrico Virgili on Astena. Astena is a mission concept for a deep study of the transient gamma ray sky and for nuclear astrophysics. Please,
yes.
Enrico, stop.
Yes.
Okay.
I can share. Can you see this? Can you see the screen?
Yes.
Let me put in the presentation mode.
Yes, presentation mode. Okay, good.
I think it's fine.
That's fine.
Okay, so let me describe this mission concept, which is called Astena. Use an acronym, as you see here, is devoted to transient events and nuclear astrophysics. The Astena was proposed in the framework of the AHED consortium, which is an European project. Now it is AHED 2020 is a continuation of this project, and also Astena also continue inside this framework. Also, Astena was also proposed in the call of the ESA Voyage 2015 with two white papers, one for transient event and one for nuclear astrophysics. The Astena collaboration is, as you see here, is composed by different institutions. University of Ferrara, for example, Piero Rosati is the lead proposer of the Astena mission, but there are also other institutions, INAF, you see several institutions of INAF, but also not only Italian collaboration. There is a European and the international collaboration with DTU Space in Copenhagen, University of Coimbra, Saclay, and many others. So in this talk, I will give a summary of the Astena mission concept, and I will describe the two instruments on board Astena, which are one is the wide field monitor with the imaging and spectrometer capability. Another one is the narrow field telescope. Then we'll describe the science that these two instruments can face, and I'll give you some example of the performance with some simulation. So as I said, the mission was proposed within AHED, and within AHED were also defined the top priority themes for the next decades, and they were nuclear astrophysics, transient event, for example, gamma ray burst. So Astena is devoted to these two topics. And actually, the recent Voyage 2020, the recent final recommendation of the Voyage 2050, as in one session, in one paragraph, as described this topic, as I have emphasized here. In the next future, we need sensitive KV to LED spectropolarimetry based on new technologies, and which allow us to detect, investigate most extreme and violent physical phenomena in the universe. And also, we have to face explosive nucleosynthesis in stellar explosion. And with the new instrument, we're going to boost the discovery rate of known and unknown rare class of transient sources. So it looked like that our instrument fits quite well this topic, which are described in Voyage 2050 final recommendation. This is the antenna configuration. This is a sketch of the antenna configuration. It's actually made by these two instruments. The red one is a Lowe lens, which is the narrow field telescope. A Lowe lens is an instrument which are narrow field, with a narrow field of view. Here are defined the properties of the Lowe lens. The second instrument is actually made of 12 modules. You see 6 blocks, 2 by 2. We have 12 modules, and this is the wide field monitor with imaging and spectrometer capabilities. So they are complementary instruments because the first is a narrow field instrument with a very deep sensitivity, very high sensitivity, and the second is a broadband instrument and wide field monitor. As you see here, we have a broadband Lowe lens as a first instrument from 50 to around 700 kV. So it is a focusing instrument that focuses the radiation at 20 meters from the lens. This is actually made with 5 meters of the body of the payload plus 15 meters, which is an extendable boom, which is feasible with the today's technologies. As you see, is written here, is as a large useful area of around 7 square meters, and the effective area is optimized for the whole entire band, but in particular for the 511 kV, using crystals at different rings in order to optimize, to maximize this effective area, this energy. The wide field monitor, as I said, is made by 12 modules with an unprecedented. Sorry. The wide field monitor is made of 12 modules, and with an unprecedented energy range from 1 kV to 20 MeV with a field of view of around 1.5 steradians. I will describe these two instruments separately. So this is the wide field monitor. As I said, we have 12 units, which are position sensitive detector based. They are based on silicon drift detector technology coupled with the scintillator bars. As I said, we have two units per side of the hexagon, which is surrounding the narrow field telescope. And each couple, as you see from here, are aligned to the same direction, and each couple is misaligned of 15 degrees with respect to the payload optical axis in order to increase the field of view of the instrument. As I said, the wide field monitor use this technology, which is made of silicon drift detector plus scintillator bar, and the technology is taken from the XGs on board Theseus, but with increased properties. Indeed, the wide field monitor has increased the effective area of 6 times the one of the XGs. This has improved point source location accuracy of around 1 arc minute, and we use square scintillator bars. We use hexagonal scintillator bars instead of squared bars. So these are the 2 XGs instrument on board Theseus, and as I said, we have 12 units. The principle of the SDD coupled with the scintillator bars is the following. Low energy are directly detected by the SDD. Higher energies, so above 30-40 kV, are interact with the cesium iodide, the scintillator, or with different material, because our baseline is cesium iodide, but we have also other material which are studied, and the light which is produced in the cesium iodide is detected with the SDD. So the SDD works as a direct detector and indirect detector. The configuration is this one. So we have actually bars of scintillator in the wide field monitor. As I said, we have hexagonal scintillator bars, and on the top and on the bottom we have a silicon drift detector. So the top silicon drift detector works as a direct detector and also as a readout system for light of the scintillator bar, while the hexagonal the hexagonal SDD only work as a readout system for the light produced in the bars. So in this system, thanks to the two-side measurement of the light, we have also the information about where is the interaction point within the bar. So this method enable a very large passband because low energy will be detected up to 30 keV. From few keV to 30 keV, we detected with the linear SDD and 3D position capability, and also polarimetry, thanks to the hexagonal shape of the bars. As I said, our baseline is the cesium iodide, but also BGO and GAG, which are other material, will be considered for the simulation we are doing now. The imaging capability of the Wi-Fi monitor is obtained with a double scale coded mask. So for low energy up to 150 kV, there is a classical coded mask method with point source location accuracy of 1 arc minute and 5 arc minute for high energies, while for above 150 kV, we exploit Compton imaging reconstruction, but using all the units, we will improve the reconstruction thanks to several units that can see the same event. These are the performances of the Wi-Fi monitor, the passband, the useful area. I'm not going into details here. You see here we have two plots. One is the point source location accuracy as a function of the signal to noise ratio, and this is the sensitivity as a function of the exposure time for different energy band. The second instrument is a Laue lens, which is very large, 1.5 meters of radius, with a huge geometric area of 7 square meters. Coupled with these optics, there will be a focal plane detector with an efficiency about 80% at 700 degrees, and with the 3D imaging capability of around 300 microns to enable also polarimetry capability with the same method as the Wi-Fi monitor, with the Compton kinematics. This is the sensitivity. This is a huge jump in sensitivity of the Laue lens with respect to other instruments. You see in this plot, the dot missions are the focusing instrument. You see also here new star. So we have maybe 1 or 2 orders of magnitude better than new star, around the same energy, and more, maybe more, if you compare the external night field telescope with the integral, which is among the other one, which are the continuum line, which are the direct view instruments. And this is the expected line sensitivity at 3 sigma with an observation time of 10 to 5 seconds, which is a 1 order of magnitude better than the sensitivity obtained with the SP at 511 kV. The narrow-field telescope is an instrument is not an instrument for survey, for wide field. Is a narrow-field telescope, so it's as a field of view of few arc minutes, about 4 arc minutes. And here you see simulations of sources, of 2 sources. One source is on axis, and the second source is with different off-axis angles from 0.4 to 1.8 arc minutes. You see that the technology of bent crystal helped to reduce the effect of coma for off-axis sources, but at above 2 arc minutes, 2-3 arc minutes, there will be a low signal for off-axis sources. As I said, coupled with the optics, there will be a focal plane detector with a minimum size of 20 or 30 by 30 square millimeter. We started with the simulation of a narrow-field telescope focal plane detector, which is made of 4 layers of cadmium zinc telluride, 4 layers which are 80 by 80 millimeters, and the thickness of each layer is 20 millimeters. And this is the efficiency, and thanks to this technology, we have 300 micron of spatial resolution in all the direction, which is capable, with which we are capable to do polarimetry. So here we just described some science that can be done with the two instruments on board Astena. This is just some example of science that can be tackled with the wide field monitor and imaging spectrometer. It can be performed, the first survey of low luminosity gamma ray burst, can be observed the electromagnetic counterpart of gravitational wave signals. We can see the X-ray counterpart of this phenomena, this fast radio burst, but we also can see unknown high energy transient sources. You can see from this paper from experimental astronomy, which is actually the first white paper that we publish at the call from Voyage 2050. But also thanks to this broadband and sensitivity and capability of doing survey, Wi-Fi monitor will be used as a monitor for trigger and follow up observation with the narrow field telescope. These are the science that can be done with the narrow field telescope. So it can be measure the spectrum of the afterglow of the GLBs. Can be observed the high energy emission of the magnetars of the sub-gamma repeaters and anomaly X-ray pulsars. We can observe a nuclear line producing type 1 supernova, for example, the 158 keV from the nickel 55 line, which is very important. And also we can detect the 511 keV, which is the line obtained with the positron electron annihilation from the galactic center. And we also can detect new sources of 511 keV energy. Just go into a little bit detail of this, a few of this point that I touched before. This is the case of magnetars, as you see here in this two plot in the passband of the Laue lens, which is around 100 keV, 1 MeV, with SPI or with other instrument, not focusing instrument, we just have upper limits. So we need more sensitive observations to detect this bump at higher energies. The second case that they want to mention is the nuclear astrophysics for the 511 keV. We still don't know which is the origin of the emission of the 511 keV.
Okay, I have one. Welcome to Day 3
Oh,
which is the emission of the which is the origin of the 511 keV. Is a diffuse emission or is due to the discrete unresolved sources? So if it's due to unresolved sources, for sure the high sensitivity of the narrow field telescope will be able to find the discrete sources which emits this 511 keV. As I said before, we are maximizing the effective area at 500 keV in order to increase the effective area at this energy using different type of crystals and diffraction orders. And the last thing that I want to mention is the very important point of the 158 keV from the nickel 56. As you see here from this paper from Roland Deal 2014, is a very low significance observation just for 150 kiloseconds of integration time. We have done a simulation with the narrow field telescope using a Gaussian and a power law as a continuum, absorbed power law with the same integration time, and we observed the same line at 20 sigma, more than 20 sigma detection significance. And with 10 kiloseconds, we see above 6 sigma of significance. So this is a very huge step forward for the possible detection of the line from the supernova type 1. As a conclusion, I would say that the STEM mission is a powerful tool to solve a question on both nuclear science and transient field, for example, in gamma ray burst. This can be done, as I mentioned, with these two complementary instruments, which are the wide field monitor and the narrow field telescope. So I conclude this my talk. Thank you.
Thank you much, Enrico. I ask if there are some questions or comments on that. I don't see. I will ask and I will comment, an additional comment to your talk. The advantage of this specific low lens, or in general of the low lenses, is the very lightweight. This is very important because the weight of this lens is about 100, this is very important, 150 kilograms or something like this. This is very important. And the other comment is that with reference to the previous attempt to build the low lens, the news is that the crystals are not mosaic crystals, but are bent crystals, perfect bent crystals with a quasi-mosaic properties. And this gives us two features. The first one is that the bend, by bending the crystals, we increase the pass band of single crystal, but in addition, we don't have the limitation of 50% of efficiency, but with bent crystals, we can get efficiency also of about 90% diffraction efficiency. These are two important issues. There are some question, not, so we can, I would conclude my chair and leaving the chair to Shaolin, Xion.
Okay.
Please stop.
Yes.
Your.
Yes.
Okay. And please, Shaolin. I don't hear Shaolin. I don't hear. Please go ahead. I don't hear you. Okay, so in this case, probably it's better to continue while Shaolin will restart his connection. And I invite Miguel Moita to go ahead with the polarimetric prospects of a new heart X soft gamma ray space mission for the next decades.
So hello everyone. Thanks for this talk. So my name is Miguel Moita, and I'm here to present the polarimetric prospects of a new RDEX soft gamma ray space emission for the next decades, which is the Astena mission that has been presented just in this talk before by my colleague Enrico. So first, I'm going to introduce about the polarimetry in high energy missions. This was also a little bit introduced by Marilyn Cole a few talks before. So this is very important to understand the mechanism, the geometry, and the emission process of the cosmic objects. They are synchrotron emissions, photospheric emissions, among others. And we know that that are some expected polarized sources, namely the gamma ray bursts, pulsars, the active galactic nuclei, amongst many others. This is known in the scientific community for some time, but however, very few measurements were made till now because of the technological difficulties of the polarimetric measurements. It's the photon angry nature of the polarimetry. You need a lot of efficiency of the detectors because of the dual events, and that makes the instruments with low polarization sensitivities for that. However, there have been some measurements till now, namely for the gamma ray burst. This has been also introduced by Marilyn Cole before. So this is the study test, some of the studies that has been displayed, and like it was said, there is a big wide range of results, and there is not all the results are consistent. So it's very important to increase the sample of the polarimetric measurements to gamma ray bursts, and it also, as pointed out, it's very important to calibrate the instruments and also to reduce the geometrical effects and all the systematic errors of the instruments, so we can have the confidence of the results. For the Astena mission, we also pretend to observe some persistent sources, and in the past there have been some measurements. For example, for the X-ray binary segments X1 that has been measured by the integral SPI, and also to the Crab pulsar that has been measured by the IBIS for the SPI aboard of integral, and also for the CZTI that made the most precise determination of the pulsar enabled polarization. And it was possible to make with this instrument time resolved analysis. How can we measure the polarimetry? This is possible because the component scattering process presents a dependency on the polarization direction by the Klein-Nishima differential cross section. So as you can see, there is the azimuthal angle over here. So when a linear polarized beam generates an asymmetry in the azimuthal distribution of the content events. What happened is that when you have an polarized beam, the azimuthal distribution, it presents this circular shape, but when it increases the linear polarization, it will become this bounty shape, the azimuthal distribution of the Compton process. For a detector, we detect these Compton events, the double events, and we make first with a scattering map. So we put the first interaction on the center, and then the second interaction along the rest of the detector. This represents a direct representation of the polarization, and it presents this bounty shape that I showed before of the azimuthal distribution. After this, we can draw then the modulation curve, as you can see on the bottom, and where we can extract the parameters as the polarization angle and the polarization level. So there are two figures of merit in order to evaluate the polarimeter. And the first one is the modulation factor that makes an evaluation of the minimum maximum of the modulation curve. So it evaluates the amplitude of this signal. And also the minimum detected polarization, which is the degree of polarization detected at the 99 confidence level. We want to keep this parameter as minimum as possible. And to do that, you can see by the formula that we need to increase in a polarimeter two main parameters, the double event efficiency and also the modulation Q factor. The scanner with the instruments aboard the scanner will provide very nice polarimetric measurements contemporary with all the standard parameters as the spectroscopy, timing, and imaging. And we'll make the polarimetric measurement as a standard observation as well as the others parameters. And for the narrow field telescope, the main parameters for the polarization is they are in the focal plane detector, and it's the high detection efficiency it's very important for polarimetry, so we can detect all the photons. There is also a fine spectroscopy response, so we are able to reconstruct the Compton events in order to know if they are good events. Also, the multi-layer or 3D configuration of the detector with the position resolution of 300 micrometers. This is important to increase the resolution of the azimuthal angle distribution. And in the case of the narrow field telescope, there is another feature because of the Val lenses that will focus in the point path function. So in this case, we know the position of the first interaction. In this way, we can reduce a lot the backgrounds. In the case of the wide field monitor, the main features for the polarimetric measurements are the hexagonal shape of the scintillators that we expect to reduce the geometric systematic errors, and also have a distance between hexagonal flat sides of 5 millimeters, and also a depth resolution that goes from 8 millimeters at 200 kV to 7 micrometers at 10 MeV. With this kind of segmented detectors, 3D segmented detectors, STN will provide high sensitivity to polarization because there will be an efficiency use of the detector, and each of these detector units will act both as a scattering and as absorbent element. It also presents another feature because we know that the modulation factor is dependent on the scattering angle of the Compton events. You can see over here in this plot that the modulation factor is maximized around 90 degrees for the energies that we are studying. And with this kind of detectors, we are able to make event selection in order to maximize the Q. We can just select the events with the scattering angles around 90 degrees, and we can, on the expense of efficiency, of course, but we can maximize the modulation factor. So now I'm going to talk about the multi-color simulations that we performed. I'm going to start with the narrow field telescope. All the simulations were performed in the MegaLeap toolkit. So for the narrow field telescope, we designed this mass model. So it's a 4 layers of cadmium zinc telluride with 80 per 20 millimeter cubic. And between these CZT layers, there are 4 layers of PCB with 10 millimeters thick. For the simulations, you use a voxel size of 0.25 millimeters. The requirement for the mission is 0.3, but for the simulations, we put 0.25 in order to see how it influences. For the beam profile, we simulated the Val lenses PSF. So we simulated the cone Gaussian beam that we placed it 20 meters from the detector, which is the requirement for the STN emission, and this will provide a full width of maximum of 1.5 millimeters. And in this case, we also we made an on-axis beam, which is an approximation since depending on the energy, the narrow field the beam coming from the Val lenses will have some off-axis angle according to the energy. So this is some examples of the simulations for the narrow field telescope. You hear the results for a 300 kV, 100 polarized beam. You can see over here the bounty shape that I showed you before, and also here the histogram, the simultaneous distribution. As I said before, it's also very important to measure the polarization, to make simulations with a non-polarized beam, so you can correct any geometrical effects of the detector. And you can see over here the results for the non-polarized beam, also for 300 keV. You can see the difference between both the multi-shape and the circular shape of the non-polarized. By using these two modulation curves, we can then get the corrected histogram that you can see over here on the right. So the first study we made, it was to measure the modulation factor and the double event efficiency for the monochromatic sources. As I said before, these are the two parameters that we want to maximize. And as you can see, the modulation factor and the double event efficiency are maximized for energies around 150 till 300. The reason for this is that it's in this energy range that the cross section of the Compton scattering process will prevail in the CZT material. So we can get the best modulation factors and also the best double event efficiency. We also test for the narrow field telescope the selection of the scattering angles here 90 degrees. Like I said before, this will maximize the modulation factor. And you can see here the difference between the selection and without selection. And with the selection, we can reach modulation factors almost till 0.8, which is very high. However, there is a big decrease of the efficiency. So this kind of selection can be only possible to very, very strong sources or with very high observational times. So we also calculate the MDP for a correct type source in the NFT. So we simulated a spectrum, a power law spectrum in an energy range between 65 and 600 keV, which is the energy range of the NFT. And we calculated the modulation factor and the double event efficiency. For the background, we used the SPI background extrapolated to the low orbit where the station is proposed to be operative. And for the effective area, we compute as the product between the geometrical area of the instrument and the reflection efficiency of the lenses. So this is the results that we achieved for the energy range 65 to 600 keV. And as you can see over here, we can reach minimal detector polarizations of around 1.2% for a 10 milligraph source with 100 kiloseconds, so approximately 1.2 days. With this kind of polaritic sensitivities, the narrow field telescope will be capable of make phase resolve of polarimetric studies. So for example, for the correct pulsar that has a rotation period of 33 milliseconds, we can reach an MDP of 20%. This MDP of 20%, this polarization error of 20% was the minimum detected by the CZTI, one of the observations of the correct pulsar. So we can reach this MDP, this polarization level of with an observation time of 9 seconds. So this means that for a phase resolved polarimetric study with a resolution of 10 microseconds, we only need 8.5 hours of observation time. So this is quite impressive. So we can make the phase resolved to the studies for numerous sources. So now I'm going to talk about the simulations that we did for the wide field monitor. This one needs to be a little bit more simulations that are currently undergoing. So for now, we simulate the mass model. It's one wide field monitor unit among the 12 that my colleague just presented, and it's a 40 by 40 rows of hexagonal centimeter bars of items of cesium iodide, with a distance between hexagonal flat sides and 5 millimeters. And for the depth resolution, for now we kept it constant with 5 millimeters segmentation along the Z direction. In the top layer there and the bottom layer, we put the STDs, but for the since we are mainly interested for the higher energies, there is in the simulation, there are no triggers on SE3, only the passive material. The beam profile for this case is a far field point source. So this is one example for 500 keV. You can see here the scattering map, the hexagonal shape of the scintillators. And you can see over here the corrected modulation curve that we got for the 500 keV. So here we also made the study with some monochromatic sources between 200 keV and 5 MeV. You can see that the modulation factor for between 200 and 1 MeV, it's between 0.2 and 0.5. However, it decreases a lot for the 5 MeV. So this kind of energies, we know that will be very difficult to measure, and only in the case of a very strong transient event will be possible to with the content scattering process. We'll be able to make the polarization studies. So for the case of the MDP, we also calculate for the waveform, we also calculate the MDP for the correct type source. In this case, we divided in energy bands, and you can see that the best energy band is between 230 and 306 keV. Here you see the minimal tech polarization along as function of the observation time for three energy bands, the ones over here. And you can see here the difference between them. And for the best band, which is the 230 and 306, you can reach an MDP of 10% for just 1,000 seconds. So for the waveform monitor, there are currently some simulations underway, namely for transient events, the gamma ray bursts, and with the full detector, the 12 units of the wild film monitor. So that's what I have prepared for you. Thank you very much for your attention.
Thank you. Thank you very much. Is there any questions? So if no question, then we thank Moita. And then we welcome the next speaker. Is Pharaoh Lisa. She'll be talking about the very interesting Lao lenses technique.
Okay, thank
so
you.
Lisa, please.
I'm sharing my screen. Okay, you should be able to see my screen. Okay, so thank you, Doctor, for giving me the opportunity to participate in this conference. My talk, which will be on the technology of Lao lenses as focusing optics for direct X and soft gamma rays, and will focus on the technology of Lao lenses, which is the technology on which the instrument narrow field telescope aboard the mission Stena, which was discovered by my colleague Enrico Virgili, will be based on. First of all, what is a Lao lens? A Lao lens is a hard, soft, and gamma ray optics based on Bragg's law of diffraction. It consists basically in a spherical cap covered by crystal tiles, Tosen crystal tiles, and by using Bragg's law of diffraction, we are able to redirect an incoming astrophysical X-ray beam to a focal point. So it acts as a focus instrument for high energies. Thanks for reason linked to the geometrical configuration of these lenses, the focal distance of a Lao lens is equal to half the curvature radius of the lens itself. With this instrument, we are able to create a broadband high-energy focusing instrument, since each ring of a Lao lens gives an almost monochromatic response, whose centroid of the diffracted radiation is linked to the distance from the center of the Lao lens. By nesting multiple rings, we are able to create a broad passband Lao lens, as you can see in this example, in which you can see a Lao lens working the energy band from 150 kV to 300 kV, in which you see that the center that the innermost rings diffract the higher radiation, while the outermost rings diffract the lower energies. The choice of crystal, since it's based on crystal material, is very important for this lens. And there are various types of crystal and various characteristics that we have to take in account. First is the difference between flat and bent crystal. A flat crystal, as you can see in this image here, just redirect the beam. It redirects to a focal point, but is not able to focus. So at the end, the image produced by a ring of those crystals will be very broad, as you can see in this simulation. Cured crystal, instead, have the property to focus the radiation. And the image is very small. Point spread function of a ring of bent crystal is, as you can see here, is very small, very precise. Then it's important to discriminate between perfect crystal. A perfect crystal is a crystal in which all the diffracting plane are parallel to each other with a certain degree of precision, and a mosaic crystal, which can be seen as a crystal, which is made by thousands of small crystal tiles slightly misaligned between each other, which you can see here in this highly exaggerated representation. For our case, we choose bent perfect crystal, as they were briefly mentioned by Professor Frontera in his intervention before. We choose those types of crystal because first, the fact that they are bent make them act as concentrator of radiation and enlarge the energy passband of a single crystal. This is because since the crystal is curved, the Bragg angle of the diffraction impinging on the crystal change on the surface of the crystal, and this gives both the focus, the concentration, and the enlargement of the passband properties. Then another very important reason why we choose those type of crystal is that they have an increased diffraction efficiency with respect to both flat perfect crystal and mosaic crystal. With the flat perfect crystal and mosaic crystal, the maximum diffraction of diffraction efficiency is theoretically to 0.5. While with this bent perfect crystal, the theory shows us that we are able to overcome this 0.5 limit and to reach higher efficiency. Then, last but not least, the internal plane misalignment of bent perfect crystal, which is called quasi-mosaicity, is smaller than the typical mosaicity of mosaic crystal. So this gives us a better focalization and a smaller point per spread function. At the University of Ferrara, our laboratory at LARIX, we test one of those crystals. We test a bent crystal of germanium of size 10 times 30 times 2 millimeters squared, with a curvature radius of 40 meters, so with a focal length of half, which means 20 meters. And here you can see the experimental result, the experimental image at 150 kV. The X profile of this image, which is the focus direction, is of 8 arc second or 0.1 millimeter. So we focused from an area of 30 times 10 centimeters square, which is the area of the crystal, which was completely covered by the radiation, to an area of 0.1 times 10 centimeters square. So the focused area is 30 times smaller than the area of the crystal which acts as a lens. So with this technology, we can achieve some great results. First of all, we can have unprecedented imaging capabilities. We expect a better point spread function than coded mask imaging, which is, an example, on integral IBIS is 12 arc minute, while our goal is to reach an imaging a point spread function of 30 arc second. And this will enable us to concentrate radiation and to produce those images up to 600 kV. So we can extend a lot the energy range in which we are able to focus radiation. Then another important advantage of those lenses is that they are lightweight and very stable optics. And we expect to be able to, our lenses will be weight less than 150 kilos. And then if we combine those type of optics with an adequate focal plane detector, we will be able to make both X-ray spectroscopy and polarimetry with an unparalleled quality, as you have seen in the previous talks by my colleagues Enrico and Miguel. At the University of Ferrara, at the moment, we are studying and developing the technology necessary to build this lens with the TRIL project, whose aim is to increase the technological readiness level of LAO lenses by building a first prototype of a broadband LAO lens. This project is a project shared among different institutes, including the Italian National Astrophysics Institute, the INAF, and the CNR, the Italian Central Research Institute. And this project is composed by various tasks. The first task is to find a repeatable and affordable method to bend the crystal. Then to find a way to assemble the 4 modules of LAO lens, which, as you can see here, a module is a part of a LAO lens. And then to study a way to connect and orient the module in a single prototype. What we want to obtain is basically a fraction of a whole LAO lens, as you can see here. We are trying to build 4 modules, this section. Regarding the first task, this is done at the IMM Institute in Parma. In Parma, they are studying the way to bend various types of crystal. The crystal that we choose will be silicon germanium, are cut to obtain the 30 × 10 × 2 mm² tiles, and then through a surface lapping technique, they are bent tentatively to the curvature radius of 40 meters. In the past, this method was already tested on mosaic gallium arsenide crystal. And here you can see the result of the past crystal. Those gallium arsenide crystal were bent using lapping the surface lapping technique. And here in this plot, you can see the size of the point spread function of each crystal as function of their curvature radius. You can see that there are 2 regions. In this central region, the effect of the mosaicity of the crystal, which in the case of gallium arsenide was of 13 arcsecond, dominates, and the size of the point spread function is linked to the mosaicity. Then, as the curvature radius gets farther and farther from the goal of 40 meters, the point spread function starts to get worse. This was with the gallium arsenide, this solid black line. The dashed line instead represents what we can obtain using perfect crystal. As we said before, the quasi-mosaicity of this perfect crystal is way smaller than the mosaicity of gallium arsenide, so we expect that the PSF is smaller, but this also put a more strict requirement on the precision of our curvature radius, because we want to stay in this highlighted region. And this means that we need an accuracy at the curvature radius smaller than 2 meters. And this was made. We were successful in this part of developing the technology. First 38 crystals of germanium were bent with this technique, and here you can see the plot of the curvature radius of this crystal of germanium, and you can see that the curvature radius is all in the limit of 2 meters from the nominal curvature radius of 40 meters. So a highly precise and highly repeatable way to bend the crystal was defined and found, and this allowed us to, this is a first increase of the technology readiness of LAO lenses. Then it's important to mount those crystals onto our lens. The module assembly is done at the University of Ferrara. And first of all, we studied the required position accuracy for our lens through simulation. Here you can see the simulation of made with bent perfect crystal of germanium, nominally bent to 40 meters without construction accuracy. The half-power diameter of this image is of 50 arcseconds. If we start to have a mounting accuracy of 15 arcseconds, then the half-power diameter gets close to the 30 arcseconds, which is our goal. So to reach our goal, we need that the mounting accuracy is smaller than the arcsecond. At the moment, we are assembling this module. Here you can see a CAD image of the module we want to assemble. And at the University of Ferrara, we are gluing the crystal on a clear quartz substrate by using a low shrinkage space qualified glue. The quartz was used because it's transparent to UV light, which is necessary for the type of glue we use, and it's a low coefficient thermal expansion. And the particularity of this frame is that it's bent to the same curvature radius of the crystal, which is 40 meters. Those crystals are oriented with using a motorized hexapod with 6 degrees of freedom and with a micrometric accuracy, which we are using to put those crystals on the frame in a very fine way. We were able to obtain the first experimental image of two aligned crystals. Those two images are the single image of two crystals, which were glued on this frame. And here you can see the combined image of the two crystals together. It's an online image of the two crystals illuminated at the same time, and this is the result. So the crystals were aligned with a misalignment smaller than 50 arcseconds. At the moment, we are working of about 50 arcseconds. At the moment, we are working on further improving this technique. As you can see in this plot, which represent the value of the misalignment as function of the time from gluing. The misalignment is within plus 15 and minus 10 arcseconds after 50 days. So we are getting close to our target of 10 arcseconds, but there is still a problem of stability in time, which we are trying to solve. With the next step of drill, we are aiming first to produce about 80 bent crystal of germanium 111 with an ultra-low miscut angle of the planes to further increase the precision accuracy of our modules. Then we plan to further refine the mounting procedure of a single module. And we want also to define and test different assembly techniques to test if they give us even better performances. For instance, we want to test if it's possible to elastically bend a crystal and glue it on a curved substrate, or eventually to test some non-glue based bonding, since the glue is very critical for our application. For example, with some anodic bonding technique. And last, we will assemble the 4-module prototype in a full prototype, which, as you can see here in this CAD image. This is made with our final goal in mind, which is to finalize the technology for the narrow field telescope, which will be put aboard the Astena satellite. The narrow field telescope indeed will be a low lens, as you can see here in red, will be a low lens of 20 meter focal radius with a 1.5 meter radius. It will be made by about 20,000 crystal tiles of sequence germanium, so a lot of crystal tiles. And we'll have an energy pass band between 50 and 600 kV. The field of view of this instrument will be about 4 arc minute, and And we expect that we'll be able to reach enough power diameter for the image produced by this instrument of about 30 arc-second. This, coupled with an appropriate cadmium zinc telluride focal plane detector with a detection efficiency bigger than 80% and a 300 micrometer spatial resolution, will allow us to make a lot of new exciting science with this instrument. So with this, I finish my presentation. I give you some further readings in case some of you may be interested in both the narrow-field telescope, the Astena, and the technology of flower lenses. Thank you for your attention. If you have any question, I'm here. I'm happy to answer.
Great talk. Thank you. So could you remind me what is the detection efficiency of this focusing?
Of the lens? Yes, of the lens. Yeah, it depends on the energy. It varies from a maximum of 0.8, 0.85 for the energy between like 100 kV and 300 kV, and then it drops a bit at higher energy to 0.3, 0.5, going toward the limit of the 600 kV. With calculated with band perfect crystal of silicon germanium optimized into different regions. Silicon is optimized for the lower energies and germanium for the higher energies.
So, Lisa, in percentage, which is the efficiency. So you mean that
yeah.
is 80%?
Yeah, 80%. Yeah, 80% at lower energies, with lower meaning up to 300 kV, and then start to decrease a bit to like 30–40% at the higher energy.
Okay, thank you. So is there any other question for Lisa? Okay, thank you, Lisa. So next speaker is Lorenzo Amati. He's talking about disease and other opportunities. Welcome.
Hello, thank you very much. Thank you to the organizers for giving me the opportunity of presenting the XGIS instrument, X-gamma ray imaging spectrometer, that was developed for TGUS, for the phase A study of TGUS, but as I will discuss, is also an instrument which could be accommodated on other missions, and actually it's really one of its main advantages that it can be redesigned very easily, and all the big heritage, technological and scientific heritage behind the study of this instrument for TGUS can be fully exploited for other mission opportunities. So, of course, I'm talking about the large collaboration, so the TGUS International Consortium, and specifically the XGIS Consortium, which is led by Italy. Both the TGUS and the XGIS Instrument Consortium are actually led by Italy. So TGUS, which stands for Transitory Energy Calendar Universe Surveyor, is a space mission concept aiming at fully exploiting the high potentialities of long gamma ray bursts for cosmology. So very shortly, as you can see on the sketch on the bottom left, these events can be detected up to very high redshift because they are hugely luminous in the X and gamma rays. And in a few cases, we were actually able to catch their fading afterglow, so the fading emission following the burst in the multi-wavelength fashion, especially in this case in the near infrared, and do the redshift of their host galaxy. And actually, at least 6 or 7 of them were identified at redshift 6, which means the first billion years of the universe. And actually, the farthest away is at redshift 9.4, which is only a few 100 million years after the Big Bang. We are talking about a probe, gamma ray burst, that can pinpoint the explosive death of very massive stars, the first stars in the universe, the so-called Pod 3 stars, they can unveil the bulk of the population of primordial galaxies, which are other way invisible or below the detection threshold to even the larger facilities in the optical and near infrared. And so also give clues not only on the first structure formation and evolution in the universe, but also to the cosmic ionization. All of these are main issues, main open issues in the early universe cosmology. To this kind of science, gamma ray burst, the long gamma ray burst, could provide really a very strong contribution, complementary to the expected advances that will occur in the next years, thanks to JWST in the near infrared, or ELT in optical near infrared, or even SKA in the radio. On the other hand, gamma ray bursts are also a key phenomenon for multi-messenger astrophysics. We know, you can see on the right, the first gravitational wave signal detected from a neutron-star merger, so a merger of a binary neutron-star system, sketched here in this figure, in this cartoon, was expected actually to produce both gravitational waves and also a short gamma ray burst. And actually this was demonstrated in 2017 with the beautiful detection of this gravitational wave signal and detection only 1.7 seconds after the gravitational wave signal of a short gamma ray burst in a direction consistent with that of the gravitational wave. So this, together with the detection also of the kilonova emission in the near infrared, which is a near infrared emission, again, produced after the merging of the two neutron stars, when very neutron-rich material produces the formation of very heavy elements, and the radioactive decay of these elements produces the near infrared emission. So all this picture, of course, gave rise to the birth of the multi-messenger astrophysics. The TSU's mission concept was developed and proposed to ESA in 2016 in response to the call for the next M5 mission. So, as you may know, the European Space Agency, similarly to NASA and other big agencies, has a space astrophysics and solar system exploration program, which is called Cosmic Vision, in which there are included small, medium, and large mission, depending on the budget, which reflects on the actual size of the mission and the scientific capacity of the missions. It was selected together with other two missions for a phase A study that went on from 2018 and 2021. So it actually ended only 1 or 2 months ago. At the end, TSU's was not selected. The phase A was very successful. It was a very difficult decision between TSU's and a mission to Venus and Vision. At the end, it was after very debated discussions, they decided to select the mission to Venus. But in any case, it was really a great success to have TSU studied by ESA for 3 years, and this opens many perspectives for further exploiting and further developing this mission concept and the instruments that were proposed for these instruments. The consortium was led by Italy, as you can see here, together with UK, France, Germany, and Switzerland, and with contribution by other European countries. So I'll go quick, but if you want to get more details on the TSU's mission concept, the science case, the expected performances, the instruments, you can go to the TSU's consortium website that you can see here, and you can find easily in the literature, in the web or on the archive, the many papers that were produced in the very last years by the TSU's consortium on the science case, again, and on the technology behind the mission. So again, very summary, the core science goals of TSU, as I said, is to get a statistical sample of very redshift gamma ray bursts. So this means 40, 50 gamma ray bursts at HE3 at least in a few years of operation, and possibly more, because these missions we know last many more years with respect to the nominal duration. So allowing the full exploitation of gamma ray bursts for cosmology, and at the same time provide, as I mentioned, substantial contribution to multi-messenger astrophysics not through short gamma ray bursts, but not only, also through the capacity of detecting, localizing, measuring the redshift, and characterizing in a multi-wavelength fashion many classes of transient, high energy transients in the sky. And of course, a key asset of Theseus mission, or missions like Theseus, which are actually under study in several other countries, or in the US, for instance, also in Japan, is the synergy, the great synergies that such a mission would have with all the very large facilities that are being built in both the electromagnetic domain. So, for instance, the extremely large telescopes like ELT or TMT in the optical, of course, SST again in the optical, which is going to be operative very soon, the SKA in the radio, CTA at very energy, ATIN in the X-rays, as well as the gravitational wave detector. So the advanced second generation and the third generation gravitational wave detector, as well as next generation neutrino detectors. All of these facilities, including their core science, gamma ray burst, high energy transients, multi-messenger astrophysics, and even cosmology with high redshift gamma ray burst. So clearly, they would benefit substantially from a mission like Theseus for fulfilling completely their science cases, their objectives. So how it would be possible for a mission like Theseus to fulfill these ambitious science goals? The concept is to overcome the current limitations, of current facilities in space and on ground, and the synergy between them. First of all, improving substantially the capability of these missions of detecting and localizing and measuring the redshift of any kind of gamma ray burst. So extending substantially the energy band on which gamma ray burst and other transients can be detected. So going much softer with respect, for instance, to Swift, Fermi GBM, or even Conus wind, and possibly even at higher energies. So going from soft gamma X-rays up to the soft or medium gamma rays. And at the same time, substantially reduce the observational inefficiency that are in the process that leads eventually to the identification and the measurement of the redshift of gamma ray burst, but also to the detection of near-infrared counterparts like kilonova emission for multi-messenger events, as I mentioned before, neutron-star mergers. And this can be done only by putting on board, so giving to the spacecraft autonomous capability of fast follow-up of the detected gamma ray burst and transient in the near-infrared. So this is the basic concept of Theseus, and this is the payload that was proposed. And actually, I have to say, the Theseus consortium is still going on in view of future perspectives. So it is still, as I said, alive, going on by itself, but also in view of possible synergy with our mission of opportunities. Sorry. So the payload, the scientific instrument suite, sorry again, included a set of monitors, so a soft X-ray imager, which was based, is based on microchannel placed optics in so-called lobster eye configuration with silicon silicon detectors, CCDs or CMOS, in the focal plane. And this is sketched in the top right. This kind of cameras, which are, by the way, the same cameras that are going to be flying on Einstein probe, for instance. They provide an unprecedented and impressive combination of huge field of view and sensitivity, because they can focus soft X-rays up to 5 keV over several hundreds of square degrees. So when we think of focusing telescope, or focusing X-rays, for instance, we think of a field of view of alpha degree. 1 degree is already a large, very large field of view. Here we're talking about hundreds of square degrees. So for Theseus, we proposed 2 of these cameras covering a 0.5 steradians. This, of course, provides the required leap in sensitivity in the soft X-rays, which is of fundamental importance for many classes of transients, and also for high redshift gamma ray burst, because of course we expect this very redshift gamma ray burst to be softer and weaker with respect to those at lower redshift. On the other hand, these cameras are limited to 5 keV with very small effective area, so only very small photons you can detect, especially from short gamma ray burst, are not. You cannot call this instrument a gamma ray burst monitor, of course. This is mostly an X-ray survey or monitor. So you need a real gamma ray burst monitor. And for Theseus, this was the X gamma ray imaging spectrometer, which by exploiting an innovative coupling between silicon div detectors, which work from 2 to 30 keV, and crystal scintillator detectors, so to extend the energy band up to the several MeV, as I will describe, we'll go into detail later on. This allows a unique energy band with very large effective area from 2 keV to 10 MeV, which is better with respect to any other gamma ray burst monitor, past, present, and even future. And this detection plane can be made of pixels, so this is a position-sensitive detection plane, and you can get imaging, so source location accuracy capabilities through a classical coded mask system. And then the onboard infrared telescope was a 70 centimeter primary mirror telescope in off-axis coarse configuration, granting a large field of view, 15 per 15 arc minutes, so to be able to include the larger region which may be provided by the two monitors, which is of the order of several arc minutes. At the same time, having the photometric and spectroscopic capabilities right, so well tuned to be capable of detecting, localizing to arc second, and measuring the redshift on board of most of the gamma ray burst and transit detected by the monitors. So as of course the X gamma ray imaging spectrometer, XGIS, is the main subject also of this talk, so I will provide more details in the next slides. This slide simply summarizes the outcome of the phase A study, the industrial phase A study, because as you may know, ESA usually adopts the approach to appoint the industrial study, so the study of the spacecraft design and the period accommodation to two different industries in parallel. For TSUs, they were Thales Alenia Space in Italy and Airbus Defense Space in Germany, and they came up with these two designs that you see, where in the red circle you see the accommodation of the two XGIS cameras. At the end, the spacecraft was designed for a launch with the Vega C, the European Vega C launcher, for a low Earth orbit, a near equatorial low Earth orbit, which would minimize the level and the fluctuations of the background, the particle-induced background. Especially, this is very important for the XGIS. So just to give an idea of the capability of TSUs, for instance, for the high redshift universe, so for the case of exploiting eventually gamma ray burst for investigating the early universe, this is the current situation with, despite many efforts from space and ground observatories, gamma ray burst missions in the space, robotic and large telescopes on the ground, we are still stuck with this situation. Only a few gamma ray bursts at HE3, as you can see, these are the gray points, the gamma ray burst with a measured redshift up to now in the last 20 years or more. This is in the cosmological context, and with TSUs, in only 3.5 years of operation, we would get this kind of results. So really a statistical sample of gamma ray bursts at HE3 and hundreds of gamma ray bursts at lower redshift with measured redshift and full characterization of the prompt emission and the near infrared afterglow emission over an unprecedented energy band. At the same time, as I mentioned before, such an instrument suite and mission profile, so such a mission, would provide a substantial contribution to time domain and multidimensional astrophysics, because it would be capable, again, to detect, localize, characterize in a multi-wavelength fashion most classes of high energy transit, and especially, for instance, those associated to gravitational wave sources. Again, for gravitational wave produced by neutron star black hole mergers, which you know are up to now the most easily detected gravitational wave sources by the current and near future gravitational wave detectors, the interferometers on the ground, so LIGO, Virgo, Cagra, and so on. And for this kind of sources, you could detect, localize the short gamma ray burst, but also the possible soft X-ray emissions that some models expect from this kind of sources. So let's specifically focus now on the XGIS. The XGIS, as is summarized here, plays a main role in this kind of mission, because as I mentioned before, even if you have on board the soft X-ray cameras, these lobster cameras, which are a baseline monitor for all these mission concepts similar to the JES that are being proposed, they are clearly not gamma ray burst detectors. So they have very many disadvantages as gamma ray burst detectors. So you need an instrument like the XGIS for extending the energy band from few keV to several MeV, or at least to cover the typical energy range of gamma ray burst, to provide confirmation and significance even to the trigger from the detection by the soft X-ray imager, where you expect many false triggers, many false signals from star flares and other sources. So gamma ray burst in that energy band is very weak, weak compared to other sources. And also, of course, you get much more. You get short gamma ray bursts that you cannot detect with the soft X-ray imager like lobster eye cameras, because these are very short and hard, spectrally hard event. And of course, you need this coverage of energy band if you want to characterize, to compute the luminosity, the radiated energy, to characterize also this very energy gamma ray burst. And of course, if you want to do science, physics with this data. For instance, it is, again, the combination of these software monitors with the XGIS and with the follow-up capability, autonomous follow-up capability of a mission like TSIUS in the near infrared, that provides the mission the capability of detecting, localizing, characterizing and measuring the direction of any class of gamma ray burst, as you can see in this spectral peak energy, peak flux, which means spectral hardness versus intensity of the gamma ray burst. As you can see, if we consider, for instance, the popular Fermi gamma ray burst monitor, the red points, it is clearly the bulk of the population of soft, weak gamma ray burst, which include high redshift gamma ray burst, but not only, also nearby short gamma ray burst associated to gravitational signals, which are expected to be very off axis because they're expected to be collimated. And given that they are very nearby, it is very likely to detect them off axis. So again, weak and soft due to, of course, Doppler effects. And this, all these events are clearly outside the capability of current detectors. So what is some more details on the XGIS? I already summarized before the concept of the detecting element on the detection plane. Here, this is a design from the phase A study of TSIUS. You can see details on the detection plane and on the imaging system. So again, the detection plane, the pixel, so the basic detecting element, again, is a pixel with a section of 0.45, sorry, so more or less half a centimeter. Which is composed by, again, a square section of a silicon dip detector coupled with a crystal detector, a crystal scintillator detector, which is in this case cesium iodine, but of course can also be in other, let's say, flavor of these detectors, as was also mentioned by Enrico, another kind of scintillator, GAG, and so on. And of course, the principle is that you use the silicon dip detectors at the top. There are also silicon dip detectors at the bottom. So both silicon dip detectors are used to read out the signal from the crystal scintillator, but at the same time, thanks to a double electronic chain, which is composed by a very sophisticated front-end electronics ASIC, specifically designed and tested and developed for this kind of detection element, the top silicon dip detectors are also used as X-ray detectors. So in this way, you are building a monolithic, very broad energy band detecting elements, and the imaging system is a more classical coded mask imaging system that I think you know very well. And this provides the location capability to the system. So this is to show how the detection plane is made. So this crystal, so these detecting elements are packed into 8x8 cubes that are our detection module, basic detection module, which is so made of 64 of these pixels. And you can see on the bottom right, actually a picture of a real prototype. So thanks to the phase A study of TSIUS and to support by the Italian Space Agency, the Italian National Institute for Astrophysics, and the European Space Agency, we could develop and test not only detecting elements, but already a prototype, which is currently still under testing, structural, functional, any kind of test, of course, the standard tests that this prototype are undergoing. So this means that the TRL, so the technological maturity of these detecting elements is already quite high. It's in the ESA scale about 5. So this means that we are, of course, such instrument is already is fully ready for further development and consideration for further opportunities, of course. These are tables summarizing the main budgets. An XGIS camera, as was proposed by Theseus, at the end was made by 10 per 10 of these modules that I mentioned before, so 100 of them. So it was a geometric area larger than 1,000 square centimeters. So this granted a very large effective area down to 2 kV up to 10 MeV, as I will show next. The weight of such a camera was about 80 kilograms, and the power required for each camera was more or less of the order of 100-110 watts. And the size was more or less 50 per 50 centimeter per 70 centimeter height. This is a summary of the main scientific performances. I think that the most impressive performance is shown in terms of effective area as a function of energy compared to other current main GRB detectors. As you can see, with respect to both BAT and the Fermi GBM, the XGIS would fill this gap in sensitivity and in energy band below 10 kV, which, as I mentioned before, is of paramount importance, not only for high-redshift gamma-ray burst, but also for nearby short gamma-ray burst of axis, so for the multi-dimensional astrophysics, but also for testing and understanding the physics of the prompt emission of gamma-ray burst and characterizing and detecting many other classes of transients. But still, the effective area is very high, also to the very high, up to 10 MeV. So you can see really an innovative and unique detector. And these capabilities have to be coupled with excellent timing capabilities of a few microseconds granted by both the SDD detector and by the crystal scintillator detector. And so a few hundred electron volt energy resolution from 2 to 30 kV, thanks again to the silicon deep detectors. The field of view of each of these cameras as designed for Theseus was of the order of 2 steradians. Okay, so to go again on the scientific impact of such an instrument, here I show again how short gamma-ray burst is the key electromagnetic phenomenon for multi-messenger astrophysics, and such an instrument like the XGIS, of course, was fundamental for Theseus and would be fundamental for any other mission of this kind for detecting and localizing short gamma-ray burst. And in particular, I would like to stress that the large effective area down to 2 kV will allow an instrument like the XGIS to fully explore, so to make a substantial leap in the exploration of the space of the population of local short gamma-ray bursts, which are the most likely to be detected in association with gravitational wave detectors, because we know that up to now, more or less, current gravitational wave detectors have an horizon for this kind of neutron star, neutron star black hole mergers of the order of 200 megaparsec, so which is very low distance for the typical short gamma-ray burst. And we expect that, of course, the system, the neutron star systems that are producing these gravitational waves in this local universe will also produce short gamma-ray bursts that most of them will be seen off axis, as it was actually the case for the only one that was detected in 2017. And thanks to this effective area down to very low energy, the XGIS will be capable of unveiling most of this population, as is shown in this diagram here. You can see on the right, in the previous slide, sorry, you could see the rate as a function of redshift if we do not consider the off-axis emission, but instead how it increases especially toward redshift, if we consider the capability of the instrument of detecting very off-axis gamma ray burst. But of course, such an instrument does provide also a strong contribution to gamma ray burst physics and understanding itself. So we would have with such a mission hundreds of gamma ray bursts with both measured redshift and full characterization, spectroscopy, radiated energy, luminosity, and timing over a huge energy band. And for instance, we could use these unprecedented spectroscopic abilities to test emission models, as is shown on the right, where we compare the extension of MGBM and what would be granted by Theseus. You see how many spectral features, breaks, and so on, which are crucial for testing models of gamma ray burst could be detected by the GIS. And on the bottom left, you see instead the capability of detecting possible absorption features, which were detected with marginal or low significance already by TZ, by Beppo-Sachs wide-field cameras in the late 90s, early 2000s. And Theseus could detect, characterize, and even use these features not only to characterize the circumburst environment and so to get clues on the progenitors, but also to measure the redshift in the X-rays. Of course,
sorry, also, 1 minute.
Yeah,
1 minute.
Yes, yes, I'm finishing. Thank you. So this is to show also the great capability of the GIS for the more general time domain astronomy. On the left, you see the sensitivity for different assumptions on the power of spectrum of sources as a function of time, and on the right, you see a simulation of a spectrum of the GIS plus also the soft X-ray imagery in this case. Simulating spectral models of soft gamma ray repeaters, which, as you know, are found to be associated at least to a fraction of both fast radio bursts and short gamma ray bursts. So I would like to remark that in addition to these unique capabilities, so that for such a kind of mission like Theseus and other mission concepts similar, it is a fundamental role. The sensitivity, so the great effective area of the GIS down to 2 keV would also grant the capability to the instrument of detecting and localizing very redshift gamma ray bursts. So it is true that many missions, also Theseus, included the soft X-ray cameras, the lobster eye, right, or mostly for the high redshift. But it is also true that the simulations done for Theseus and also for other studies show that actually the number of gamma ray bursts that could be high redshift gamma ray bursts that could be detected by the GIS alone, so without the lobster eye, and with a location accuracy as good as better than 5-6 minutes, is competitive with the one that could be detected, that could be detected by the soft X-ray camera. So the message here is that actually this is with a camera and instrument like the GIS, you could do everything, both not only the short gamma ray burst, the multi-messenger astrophysics, the gamma ray burst science, and so on, that you cannot do anyway with the lobster eye camera, but you can also replace the role of the lobster eye cameras also in the identification, the localization of very high redshift. So just to conclude, I already now summarized the scientific relevance of this instrument. I also shown the great progress that was done during the Theseus phase A study in the technological advancement and study of the instrument. So I would remark that thanks to the great flexibility, the modularity of the detection plane concept and the great flexibility in the design would allow the design of the GIS instrument to be adapted to different possible scientific objectives and available resources on next generation space missions. So I'm done, and thank you very much. So I take some questions if any, if there is time. So Shaolin, I finished.
I don't hear Shaolin. Shaolin, do you have a problem? Anyway, Lorenzo, thank you very much for this very interesting talk. Our best wishes
of
for
course,
the success. Oh, Shaolin is there, please, Shaolin. Shaolin, We don't hear you. Anyway, I suggest now, because we have to go ahead, suggest to start the last speaker to start his talk, MAVCube, a novel computer camera and MAV GRO. Wenxi Peng, are you there? Please. We don't hear you. Wenxi Peng, we don't hear you. Please activate the audio. Wenxi, we don't hear you. Shaolin? Peng? Peng, please connect. We see your screen.
Hello?
Please. Wenxi Peng?
Hello?
Hello, Shaolin. Okay.
Yeah, can you hear me? So
yes,
I think when she's reconnecting, I
yes.
think he's reconnecting.
Okay. Wenxi Peng is still not connected.
I think he has some problem.
Here.
I'm sure he is connecting. Just a moment.
Okay. Okay, please. We see a number instead of the name.
Yeah, I think
61150.
Yeah. But we can't hear you, Wenxi. We can't hear you.
Yes, we hear you.
We can't hear you.
With you, everything is fine. Is Peng, which is not Peng audio. Shaolin, Wenxi Peng is in your institute as well? Shaolin? Okay, Wenxi Peng. We see the screen. We don't hear anything. And this morning, everything was nice. I don't know how to. Shaolin, are you there? Are you connected again?
I have the feeling there's a problem with the Wi-Fi at IHEP or the general internet there, because they all seem to have issues at the moment.
We have, I don't know how to, probably they have to reconnect to close. Merlin, you know better which are the problems with China.
No, I'm just guessing that the internet is bad there at the moment. It happens sometimes when you're at IHEP.
Yeah, Filippo, there is a message in the chat by Shaolin saying that Peng is reconnecting using
yes, I see now.
So yeah,
it's reconnecting using another computer.
Yeah, so we can wait a bit, hopefully.
It's a pity. If there is somebody who want to put question to Lorenzo Amati or to other speakers, please. Everything is clear. Okay. PWX, okay, seems is connecting. Peng? Shaolin?
Well,
do you hear us?
Yes, actually, Filippo, so Peng, both Peng and Shaolin are not muted, so we should hear them. If you see, there is the microphone moving from, so it seems that they are talking actually, but as they are unmuted, so it's really.
No, Shaolin has the muted.
Now yes.
The microphone.
Now yes, but he was talking.
And if I send him a chat, the answer is that is not connected. This is very strange. Shaolin is not in this meeting. And this is Peng.
Yeah.
Peng. Wenxi Peng. We don't hear you. Also, Shaolin is not connected. Is there, but there is no.
Enrico is suggesting to Peng to try to work on the volume of the microphone, maybe.
Your volume level is maybe too low. Ah, probably, I don't know.
It's just a possibility. It's strange that we cannot hear both of them, no?
Yes.
Are they connected from the same institute or otherwise?
I asked, but he didn't answer. Shaolin? Peng is there, but Shaolin? They have a problem, obviously. I am writing to the chat. We don't hear you. Huh. I don't know how to. We are doing all the. I'm writing them continuously in the chat. I can hear you. I can hear you. I don't understand, but we don't hear you.
Filippo, maybe we can suggest Peng to show in any case the slides, even just to, he can stay some seconds on his slide and we can have at least a look at.
Yes.
Okay. So Peng, if you could show your slides, at least we have a look at the presentation.
Yes, yes, yes.
Stay a few seconds on each slide. Yeah.
I sent him a chat, a message. I have, Merlin, I have to leave. If he can upload this slide in Inteco, be great. Thank you all. I don't understand how to go ahead. In a short time, we need to conclude. Let me send a message also to, I don't hear, but it's very strange. I don't see in the chat Shaolin. Yes, yes, we see the slide. We see the slide. So we see the screen, but not your voice. Go ahead with the slides. Okay. So for word, MEV cube, gamma rays provide the clearest and direct insight. No, this you show. This is likely a gamma ray telescope. Here it shows the goals. And now Chandra, Comptel, and the next generation mission in this energy range. What they expect. Very good. Scientific objective. Galactic center mystery. Compact object, nucleosynthesis, AGN, gamma ray burst, and others. Good. Yes, uncompact objects, which are the possible goals. Observatory mission, Astrogan and Amigo. Other mission, Dual, COSI. Most work in the Compton telescope and the Pale Production telescope. The Chinese mission for high energy astrophysics. Polar, JECAM, HXMT, DAMPI. And this could be heard And this is a Pathfinder mission. So seems to be similar to the concept of an astrogan. 10, 20 layers, CZT pixel, energy range, 250 kV, 5 MeV, any resolution less than 3% at 662 kV, spatial resolution less than 500 micron for silicon, and 2 millimeter less than 2 millimeter for ZT, which is the angular resolution is not provided. Design and prospect performance, 10 layers. Only modify the pitch, 20 layers. And this is the use of CZT. And then the effective area in square centimeter. Compton effective area this one from 200 to 200 kV to 5 MeV. Compton effective area is this one from 1.5 to 1.1 square centimeter. This is, I imagine, for a single unit. R, and this is CompTel. This is CompTel. This is the new, the MEF cube, 12 units. This is so it's a microsatellite, microsat. Very nice. Detector design. This makes use of CZT detector, 4 times 4 units. It's an array. This is the new concept. 2017, we proposed a mission called the MEV Gamma Ray Observatory to CAS, to the Chinese Academy of Science, and Strategic Priority Program of Fund supported our preliminary research. This is a mini sat or microsat, better. 6th layer of silicon detector, I suppose. Colorimeter, seismoiodine, GAG, bar, anti-coincidence detector as well. On the top, imagine, and on the lateral shield, the lateral side, and the cosmic burst monitor based on on lanthanum bromide plus SDD, and then MegLib performance study using, I suppose, MegaLib probably, and G4 tools. And this is the expected energy resolution. I see here around few kV. With a low threshold, there are more than one detector. The low threshold detector of the GCT is 10 kV. Calo is based on lanthanum bromide, cesium iodine, GAG, one of these, with the low energy threshold 20 kV, and the ACD, which is a position center detector, thickness 6 millimeter, low threshold 100 kV. So probably they have several detectors, 3 types of detectors that cover the band. So a broad band. The effective area is shown here. This is not clear how to achieve this very high effective area, because at the beginning we found a very lower effective area, and now they talk about for more than 1,000 effective area. And here there is the angular resolution. I don't see the scale. Angular resolution in sigma is 2.5 degrees. This is and arrive to 1 degree. Okay, so the angular resolution is from 1 degree, more than 1 degree. This is for polarization. And this is the measurement expected capability to measure the polarization at 800 kV, assuming 100% polarized flux. And the optimization parameters are shown here. Without lateral calo, we have not understood completely, at least me, the different detection units adopted for this mission. But what we see is an effective area of 86